So in this video we're going to continue talking about the lattice structures in crystalline solids, and in particular we're going to talk about the lattice structure of alloys and of ionic compounds. So we had previously talked about a class of alloys known as substitutional alloys, and the example given was that of bronze. And in a substitutional alloy, what we do is we just switch one of the atoms that's in our crystal for another kind of atom. And as long as the atom that is substituting is within about 15% of the radius of the other atom, then that alloy will be stable. There's another important class of alloys that are known as interstitial alloys, and in these cases what happens is the non-host element will occupy holes in the crystal lattice of the host element. So we're going to just look at holes in two different types of unit cells: the simple cubic unit cell and the face-centered cubic unit cell. And you can see that there's a pretty big hole right in the middle of the simple cubic unit cell. When you look at the face-centered cubic unit cell, you can see there's all kinds of gaps all over the place, but they're a little bit smaller than what we're seeing in the simple cubic unit cell. So we're going to look at three different types of holes. The first hole that we're going to look at is what's called the cubic hole that sits in the middle of the simple cubic unit cell. And an atom that would be sitting in this hole would be surrounded by 8 atoms in the lattice of the host located at the corners of a cube. When we go to the face-centered cubic unit cell, it gets a little bit more complicated. The first type of hole that we're going to look at is what is referred to as a tetrahedral hole. And the tetrahedral holes are so called because an atom that's in one of these holes is surrounded by 4 other atoms directed towards the corners of a tetrahedron. So it's a pretty small atom that's going to go into one of these holes. Where these holes are just behind each corner atom, so they're a little difficult to see. So you get one tetrahedral hole behind each corner atom. That gives you 8 of these holes per unit cell. The third kind of hole that we're going to look at is also in the face-centered cubic lattice, and this is the hole that lies halfway along the edges of the unit cell. It's pretty kind of visible when you look at this. It's called an octahedral hole because an atom that is in one of these holes is surrounded by 6 other atoms directed towards the corners of an octahedron. There's also one of these holes right in the very middle of the unit cell that is surrounded by the 6 face-centered atoms. So previously we were discussing the structure of the alloy steel, and in steel what we have is a face-centered cubic array of iron, and then the carbon atoms sit in these octahedral holes. So these holes have different sizes, and perhaps not surprisingly, the biggest of these are the cubic holes. And the cubic holes can be up to the size of the host. So the cubic holes run from about 0.7 to 1 times the size of the host. The next biggest hole are your octahedral holes that we see in the face-centered cubic lattice, the ones that are halfway along the each edge and in the center of the unit cell, and these guys are about 0.4 to 0.7 the size of the host. The smallest holes are those 8 tetrahedral holes that lie behind the corner atoms of the face-centered cubic unit cell, and these guys are 0.2 to 0.4 the radius of the host. So it's important to think about how many holes of each type we get in the unit cells. So there is 1 cubic hole right in the middle of the simple cubic unit cell, and 1 atom can go in there, and that atom will not be shared with any other unit cells. So there is 1 cubic hole per unit cell, and you get 1 atom for it. So if you put an interstitial atom into every cubic hole, because you get 1 atom for a simple cubic unit cell, and then you're going to get one cubic hole right in the middle there. If you fill all of those holes, you'll get a 1-to-1 ratio of host to non-host. It's a little bit more complicated to think about how many tetrahedral holes there are because we can't obviously see them. They lie behind each of the corner atoms. There are 8 corners, and these atoms are internal to the unit cell, so the atoms that are in these holes will not be shared with any other unit cells. So there are a total of 8 tetrahedral holes per unit cell. So as there are 4 atoms in a face-centered cubic array per unit cell, if you fill all of these tetrahedral holes, you would end up with a 2-to-1 ratio of holes to the atoms that are in the FCC lattice. Octahedral holes is a little more complicated to count up how many holes there are. There's one hole that lies halfway along each edge, and then there's this hole that sits right in the very middle of the unit cell. So if you don't remember, there are 12 edges to a cube, and any edge of a cube, when we start stacking cubes together, will be shared amongst 4 different unit cells. So we get a quarter of a hole per hole, and per edge, sorry, and there are 12 edges, so that's going to give us a total of 3 holes along the edges, and then we've got our 1 central hole, so there are 4 octahedral holes per unit cell. So if you put an atom in each of your octahedral holes, you'll get a 1-to-1 ratio of non-host to host atoms. So one way that you'll see problems about substitutional alloys is you'll be given a verbal description of the alloy and you'll need to decide the formula. So this example here kind of illustrates that. It says the unit cell of a substitutional alloy consists of a face-centered cubic array that has element X at each corner and an element Y at the center of each face. What is the formula of the alloy? So we know that a corner atom, we get, for every corner atom, we get 1/8 of an atom, and there are 8 corners on a cube. And then when we start looking at the atoms that are in the center of a face, of each face, these atoms contribute 1/2 of an atom to the unit cell. And how many faces on a cube? There are 6 faces on a cube. So we put all of that together and we calculate the number of x's, so we get 1/8 of an atom for every corner, and there are 8 corners on our unit cell, so that gives me 1x. And then my y, we get half an atom for an atom that's on a face. There are 6 faces on a cube, so that gives me 3 atoms of y. So 1x, 3y, the formula is xy3. Here's another one. It says an alloy used in dental fillings has the formula Ag₂Sn. So it looks like there's 4 atoms per unit cell. It says both tin and silver crystallize in a face-centered cubic unit cell. Silver has a radius of 144 picometers and tin also has a radius of 144 picometers. Is this alloy likely to be substitutional or interstitial? So what I need to realize here is that both atoms have the same radius. As the types of holes that are found in an FCC lattice are all smaller than 1 times the radius of the host, it is not possible for this alloy to be interstitial. Neither of these guys will fit into a hole in the other's lattice. It has to be substitutional. To be interstitial, one atom needs to have a radius of no more than 70% of the other. That would be if it was using the octahedral holes. To be substitutional, the atomic radii must be within plus or minus 15% of each other. Thus, the alloy is substitutional. Here's another one. It says an alloy comprises a host face-centered cubic metal A, so we've got 4 A's, and interstitial metal B. So B is going to be in octahedral and tetrahedral holes. It says, what is the formula of the alloy if B occupies half the tetrahedral holes? So there's a face-centered cubic array of A, so that means we've got 4 A's per unit cell. There are 8 tetrahedral holes per face-centered cubic cell, and B is occupying half of them, so we have 4 B's as well. That means that we've got 4 atoms per unit cell of A, and then because we've got half of the 8 tetrahedral holes filled with B, we've got 4 atoms of B, so the formula AB. These guys are combining in a 1-to-1 ratio. If you put A4, B4, I would be quite happy with that as well. Okay, so the second class of ionic compounds that I'm looking at in this video are ionic compounds. And we're going to look at ionic compounds composed of monatomic ions when we're looking at the structures. But it's also important to realize that ionic compounds can also be formed between polyatomic ions as well. It's ionic bonds that are holding these guys together, and those ionic bonds are very, very strong. If you look closely at some salt crystals, you'll notice that they're little cubes, and you can actually grow really big ones of these. This is kind of like palm size, the one that's being shown on the right there, and that's a kind of like just fun activity to do. So why are the crystals little cubes? Well, that's because they've got a cubic unit cell. So the unit cell of sodium chloride is really famous. It's referred to as the rock salt structure, and you'll see that there's lots of problems that are talking about the rock salt structure, and you should probably know that name. The unit cell of sodium chloride consists of a face-centered cubic arrangement of chloride ions, and then the smaller sodium ions are occupying all of the octahedral holes. So, in a face-centered cubic arrangement of chloride ions, we would get 4 chloride ions per unit cell. So, we know that we've got 4 chlorides, so then how many sodium atoms are there? Well, there are a total of 4 octahedral holes per face-centered cubic unit cell, so there are also going to be 4 sodium ions. So the rock salt structure gives a 1-to-1 ratio of sodium ions to chloride ions. And when you look at it, what's really cool about it is you can see that the ions with opposite charges are always kind of closer than those that have the same charge. And so this kind of like makes the attractions outweigh the repulsions. So this rock salt structure is a common way for ionic compounds to achieve a 1-to-1 ratio of ions. So if we look at this, we're going to say compare the radii of sodium and chloride ions. We observe that the sodium ion is actually a little too big to fit in tetrahedral holes. Remember, the ideal sort of size of an atom that's going in a tetrahedral hole is between 0.2 to 0.4 times the radius of the host. It turns out that a sodium ion is about 0.6 times the radius of a chloride ion. And so it has this has a knock-on effect, and normally for a face-centered cubic unit cell, the atoms will touch, or the ions in this case, along the face diagonal. But because the sodium ion is a little bit too big, it causes the face-centered cubic unit cell of the chloride ions to expand a little, and the atoms don't actually touch along the face diagonal anymore. They touch along the edge. So in problems concerning the rock salt structure, you might have to consider that the ions touch along the edge rather than the face diagonal. Sometimes the sodium chloride rock salt structure is described in the opposite manner, which is that there is a face-centered cubic arrangement of sodium ions with chloride occupying the octahedral holes. This is not actually technically correct because the holes, can't accommodate the larger of the 2 ions. But if you do look at the structure, it kind of has that appearance. We look at just this center plane here, and you can see very clearly that there is a face-centered array of the sodium ions, and then there are these chloride ions that are halfway along each edge. So it's not entirely incorrect, and you see that pattern repeating again in the next layer up here. The take-home message, though, is that a common way of ionic compounds getting a 1-to-1 ratio is the rock salt structure, especially when the cation is 0.2 to 0.4 times the size of the anion. So here's a really kind of like complex numerical question regarding the structure of an ionic compound. It takes a little while to work through this guy. It says the structure of lithium chloride comprises a face-centered cubic array of chloride ions. In lithium chloride, the lithium ions, which occupy holes in the structure, are small enough to allow the chloride ions to touch along the face diagonal. The edge length of the unit cell is 513 picometers. Part A of the question asks, what is the radius of the chloride ion? And then part B asks, what kind of hole do the lithium ions most likely occupy? So, because in this unit cell the chloride ions touch along the face diagonal, I know that root 2L is equal to 4 times the radius of the chloride ion. So I can go ahead and calculate the radius of my chloride ion. So root 2L is equal to 4 times the radius of my chloride ion. Divide both sides by 4, and I get my radius of my chloride ion when I substitute in my unit cell edge length. So it's 181 picometers. Okay, in the problem I'm given the radius of the lithium ion. So now I'm going to calculate the radius of the ratio of the lithium ion to the chloride ion, and it turns out it's 0.42, which is way too big. Well, you know, it's not way too big, but it's really on the big side to fit into tetrahedral holes. So what makes most sense is that the lithium ions are sitting in the octahedral holes, and that lithium chloride has the same structure as sodium chloride, or another way of saying that is it has the rock salt structure. In some ionic compounds, one ion is small enough to fit in the tetrahedral holes, and most commonly it's cations that are smaller than anions, not always. One of these structures is what's called the sphalerite structure, which is zinc sulfide. And in this structure what we have is a face-centered cubic array of sulfide ions, and then the little zinc ions occupy 1/2 of the tetrahedral holes. And so this gives a 1-to-1 ratio of ions as well, because in the face-centered cubic array of sulfide ions you get 4 sulfide ions per unit cell, and there are 8 tetrahedral holes per unit cell, and we're occupying 1/2 of them, so that means we've got 4 zinc ions per unit cell. So this is an alternative way of getting a 1-to-1 ratio of ions. It only works when your smaller ion is small enough to fit into the tetrahedral holes. This sphalerite structure is also sometimes referred to as the zinc blend structure, and yeah, it's kind of cool, right? You see that you have these 1/2 of your tetrahedral holes are occupied by the tiny little zinc 2+ ions, and yeah, it's a cool way of getting this, an alternative way of getting this 1-to-1 ratio. The third really common structure that we're going to see amongst ionic compounds is referred to as the fluorite structure. So the mineral fluorite is comprised of a face-centered cubic array of cations, this time positive calcium ions, and then the fluoride ions in all of the octahedral holes. So in a face-centered cubic array, we're going to get 4 calcium ions. As there are 8 tetrahedral holes per unit cell, we're going to get 8 fluoride ions per unit cell. So 4 to 8, that's going to give me a 1-to-2 ratio. And that makes total sense because we need 2 fluorides to balance the double positive charge on the calcium ion. So this is a way in which ionic compounds can achieve a 1:2 ratio of cations to anions. Now, it turns out that this is kind of a slightly odd structure. Calcium ions are actually smaller than fluoride ions. So in this structure, the calcium ions which are in a face-centered cubic array, again, they don't touch along the face diagonal. So these fluoride ions really shouldn't be in those tetrahedral holes. But fluoride, fluorine, it's a super electronegative element. It does weird stuff, and we're seeing kind of fluorine doing its weird thing yet again. The take-home message, though, is this structure, the fluoride structure, is really, really common where we have a 1:2 ratio of cations to anions. There is also what's called the anti-fluorite structure, and in the anti-fluorite structure, all that's different is that instead of the cation being in the face-centered cubic array, the anions are. And a good example of this is lithium sulfide, and in lithium sulfide, we have a face-centered cubic array of sulfide ions with lithium ions occupying all of the tetrahedral holes. So some questions are going to ask you about the density of ionic compounds, and what's important here is that when you're calculating the mass of your ionic compound, that you take into account that you've got more than one atom type present. Otherwise, they're kind of similar to calculating the density of a metal. So here's an example of calculating the density of sodium chloride. So it says, what is the density of sodium chloride in grams per centimeter cube if the edge length of its face-centered cubic unit cell is 564 picometers? So the first thing I'm going to do is calculate my volume of my unit cell, and I'm going to calculate that in centimeters cubed. So I've got a couple of options. I can convert my picometers to centimeters before I begin, or I can calculate the volume in picometers and then do a conversion to cubic centimeters, which is what I've done here. Either way, you should end up with a tiny little volume in cubic centimeters, because remember, this is just a handful of atoms. So now I've got the volume. The next thing I'm going to need to calculate the density of my unit cell is the mass. So I've got a face-centered cubic array of chloride ions. That gives me 4 chloride ions. And I've got sodium ions in all of the octahedral holes. So I've got 4 sodium ions. So the mass of my unit cell is going to be the mass of 4 sodium ions and plus the mass of 4 chloride ions. So the key thing here is I've got 4 ions, each weighs 22.99 grams per mole, and in 1 mole there is an Avogadro's number of ions. So this is the mass of my sodium ions, and then I'm adding to that the mass of my chloride ions, and again I've got 4 chloride ions, each has a mass of 35.45 grams per mole, and in 1 mole I get an Avogadro's number of chloride ions. So again, I get a tiny little mass because I've only got a total of like 8 atoms here, right? So this is not going to be a very big number expressed in grams. Calculating the density in grams per centimeter cubed from here is fairly trivial. I just take the mass, divide it by the volume, and I am done. So typical densities are going to be sort of, 1 gram per centimeter cube at the sort of the lower end, and maybe like 30 grams per centimeter cube at the extreme high end. Okay, so that concludes this second video. Keep in mind that you've got some work that's due early next week, but that's all you're going to hear from me for this week.